Okay, so welcome everyone. It's a great pleasure to welcome here today Professor Emmanouil Kioupakis, Manos Kioupakis, from the University of Michigan, that, by the way, will spend the academic year 2024-2025 here in Lausanne. So Manos got sort of his first step in electronic structural simulation during his PhD at the University of California, Berkeley, with Stephen Louis, working both on DFT plus U and GeO₂ techniques. And then he moved on to a postdoctoral stay with Professor Chris Van de Walle, University of California, Santa Barbara, where he worked, among other things. The work I remember very well is Auger recombination effect and rates. And he has been now a professor at the University of Michigan in Ann Arbor, where he's also the Carl and Patricia Betts Family Faculty Scholar. Among his many awards, he got the National Science Foundation Career Award, the John and Beverly Holt Award for Excellence in Teaching, and the 1938 award by the College of Engineering of the University of Michigan. So great pleasure. And I think this is our 35th distinguished lecture on advancing the state of the art in semiconductor technology through predictive atomistic calculation, from uncovering fundamental limitation to discovering new materials. Manos, the floor is yours. Very welcome.
Thank you very much. Thank you very much, Nicolas, for the kind introduction. And of course, thank you again for the kind invitation to be here today. It's my pleasure to discuss the work we do in my group on how we can use atomistic calculations to understand what are the problems that current semiconductors face and what can you do in the future to discover new materials and overcome these limits. So I'd like to start first with the early work on semiconductors. And of course, the person here you see is Wolfgang Pauli. As you know, he's covered many things, spins, neutrinos, the exclusion principle. And he's also done important work in semiconductors. Actually not. As you know, Pauli had some very vitriolic quotes about many things, including semiconductors. He did not believe it was a thing that existed. But just 25 years later, that was the Nobel Prize was given for discovering precisely what people were looking for, the semiconductor effect and the discovery of the first transistor using germanium. So I hope this serves as inspiration to those of us working with new materials, that even though people may not believe you at first, eventually things may work out and you can make a great discovery. So thanks to semiconductors, we have made huge leaps in electronics and computing. So what you see here is a picture of the ENIAC, one of the first supercomputers operating starting at the end of the war to 1955. That was where the first hydrogen bombs were simulated, run by women programmers, as you see. At the time, there was no transistors, so everything was running on vacuum tubes. And so the computer at the time had a capacity of 500 floating point operations per second. In comparison, if you have a smartphone today, that operates at 100 gigaflops, like 9 orders of magnitude faster. And if you look at our fastest supercomputers today, you get 7 more orders of magnitude. So over the years, you see we have this 16 orders of magnitude improvement in our computing capabilities, which gives rise to things like artificial intelligence and machine learning and all those capabilities we see today. And I can't think of many things in science or society where we see 16 orders of magnitude of improvement. And that's all thanks to the semiconductors and transistors. So semiconductors, it's a timeless problem for electronics and computing. It's also a timeless problem in the energy field. Famously, solar energy. Solar cells are primarily produced with silicon, the cheapest, the most available technology for solar cells. And even though today we still use primarily fossil fuels for energy, most of the new capacity installed, as you see here, is solar. Okay, so new electricity is more than 50% solar. That's for 2013. So the world is changing thanks to semiconductors. We also see semiconductors when it comes to lighting. We have been switching from incandescent to fluorescent and now to LED light bulbs, which can boast efficiencies that can exceed 80%, from electrons in the socket to photons coming out of your LED. In comparison, an incandescent light bulb has an efficiency of less than 5%. And that has had a dramatic effect in society because today, for the first time in history, the cost of photons is approximately equal to that of the cost of electrons. So we can talk about, can we do things with kilowatt hours of electrons? Can we do things with kilowatt hours of photons, right? And we can do things like indoor agriculture. So we can produce food in parts of the world where we don't have natural sunshine, right? And that's the only way we have to convert electricity from wind, from fossil fuels to food. Very big discovery, awarded the Nobel Prize in Physics. Another aspect of semiconductors for energy is for thermoelectric energy conversion, where we can use waste heat from a nuclear source to power a spacecraft, such as the latest Mars rovers, as well as the Voyager spacecraft, which are some of the farthest, objects from the Earth that we have sent, and they keep operating for more than 50 years now. So these are applications where we use semiconductors for energy. So again, a timeless problem, but also a very timely problem right now, because our whole society relies on semiconductors, and since the pandemic, we have disruptions of the supply chain, and so there's a very big motivation to boost our capacity for manufacturing, for energy efficiency, and to combat climate change. Excuse me. All right, so in order to understand semiconductors, we need to understand the quantum effects that take place between electrons, photons, and phonons in a material. Okay, so here's an example of a silicon solar cell where we send in solar photons from the top, and they can be absorbed in the solar cell. And when they get absorbed, they produce electron-hole pairs that eventually get converted to current. Electrons and holes diffuse in the material, they reach the terminals, and that gives us current outside the device, and we can harvest the energy as in the form of electricity. However, sometimes those electrons and holes that get produced, excuse me, the device, excuse me, get some water. Sorry for that. Those electrons and holes may come across another hole where they can recombine and will lose the energy in a non-radiative way. And so that is a waste process. So understanding this quantum process that take place in materials is important to understand how devices operate. And in particular, we need to understand what is the role of phonons in facilitating these processes, because they may enable processes that are otherwise not allowed due to lack of momentum conservation. So what's the process we do to understand these phonon-mediated phenomena? We start with density functional theory, where we get our basic structure, thermodynamics, and wave functions, and we can use them to study the effects of alloying or defects and dopants. But that's not enough, because we need to correct the band gap in order to get an accurate band structure and study excitonic phenomena, for example. In addition, we need to understand the role of vibrations and phonons and how the vibrating atoms affect the electronic properties and give rise to scattering. And last, we need to put this all together to investigate quantum processes and understand things like optical spectra, mobilities, radiative recombination rates, as well as non-radiative recombination in the Auger-Meitner process. So if you'd like to learn more about the specifics of each of these techniques, I invite you to read this review paper we wrote recently in the context of ultra-wide bandgap semiconductors. This is meant to be accessible both to theorists as well as experimentalists, and gives a broad overview of how density functional theory techniques can aid in the discovery and design of materials. But what I think in my work is that since we have tools today that are predictive and can predict properties of materials without input from experiments, we should go one step ahead of experiment and predict new semiconductors that can surpass the current state of the art. So I'll cover some of that in my talk today as well. All right, so today's talk has three themes. In the first, I will discuss quantum processes, in particular, how phonons enable optical absorption in materials. In the second theme, I'll discuss how phonons also enable Auger-Meitner recombination in many materials, including silicon. And last but not least, I will discuss how we use theory to discover new semiconductors for power electronics that have ultra-wide bandgaps and can overcome the limitations of many of the current materials. So we'll start with absorption first. And I want to first motivate why we need phonons when studying optics. So if you look at how semiconductors absorb light, is that when the photon comes in, photon gives us energy, but not much momentum. So in this energy momentum band structure diagram, the electrons undergo a vertical transition from the valence band to the conduction band. So that's a one-step process. And today we have very powerful codes that can include the effects of temperature, the effects of excitons. We can understand all these effects with very good agreement with experiment. However, everything you see here happens for ultraviolet light, not for the visible. But as we know, silicon does absorb in the visible. That's how solar cells operate, right? That's the key operation behind solar cells. In order for silicon to absorb visible photon in the spectral region between its indirect and direct band gaps, we need phonons. Okay, the electrons need to collide with the vibrating atoms, get some extra momentum, and enable a transition across the indirect band gap. Just to make it clear, if the atoms in silicon could not vibrate, silicon would have been transparent, and you would not have solar cells. All right, so the way we do this is we do perturbation theory. So if you want to start direct absorption, we start by taking the electron-photon interaction to first order, where this is the Hamiltonian describes the electron-photon interaction. We can use expressing them in terms of the momentum operator or the velocity operator. And we can use this in Semiconductor rule to find the rate of the probability of transition from the initial to the final state per unit time. Our initial and final states as the electron plus the photon, and we can convert this to the absorbed power by taking into account the photon energy, and by taking into account the incident power as well. We can convert this to the absorption coefficient. And understand this is a long equation. I don't expect you to look at every single piece here. The important thing is we need to do a sum over the Brillouin zone of energies, energy differences, occupation factors, and the optical matrix elements. And if you do also the Kremer-Koenig transformation, you can find the real part, and that also gives you the refractive index. And that set gives you the entire optical properties for your material. All right, now when it comes to phonons, if you want to look at phonon-assisted optics, you need to use second-order perturbation theory, where now your Hamiltonian is both the electron-photon and the electron-phonon interaction. And so here we need to go to second-order Fermi's golden rule and keep only the cross terms that describe the phonon-assisted optics. So higher order perturbation theory. And so here then the key equations, I know they get a little bit longer, but you can find the imaginary part of the electric function that involves this double sum over initial final states. We still need to conserve energy through this delta function. What changes now with phonons is we have these new matrix elements that are composite. They consist of the electron photon matrix elements and the optical matrix elements. And they can involve two paths that involve going from the initial to the final state through some intermediate state along paths S1 and S2. And again, once you have the imaginary electric function, you can translate the absorption coefficient through this simple relation. So what's the challenge? Everything we see here can be done from first principles. In fact, you can calculate any of these terms on your laptop in 5 minutes. The problem is that we have many combinations to take into account. So when you look at direct absorption, we just have a single sum from the valence to the conduction band. But when you have a phonon-assisted process, we need to consider every possible initial state going to every possible final state, and that number of combinations is just very large, about 200 million. So even on very large supercomputers, this constitutes a very sizable challenge. So what do? We learn the method of interpolation, the method that Nicola pioneered in the 1990s and early 2000s, where basically we transform from the Bloch to the Voignet basis, and that allows us to interpolate the key quantities to arbitrarily find grids in the Brillouin zone. And those are the electron energies, the optical matrix elements, but primarily the most difficult part, the electron-phonon coupling matrix elements, with a method developed by Justino and others, and are now implemented in the EPW code. So with all that together, we find that we can predict indeed accurate phonon-assisted optical spectra across the indirect bandgap of silicon, which gives us the absorption edge now across the indirect bandgap. I need to note here that we have slightly shifted the bandgap to match the experimental absorption onset because we don't have such accuracy with DFT or the GW method to predict these small variations to the bandgap. But most importantly, we also find how the absorption spectrum varies in the visible range. So that gives us the key quantity, the key result about how silicon absorbs visible photons, which was for the first time we're able to obtain this quantity. So the data you see here from experiment is 50 years old, and we're able to come with theory and explain them. I want to note that this capability is available in the public code, the APW code, where you can download and use it, and it's readily available. And you can see more details in the latest paper that is posted on the archive. All right, so we can take this method and we can apply it also to other semiconductors with indirect band gaps. And the famous case is silicon carbide. Now, silicon carbide has many polytypes. And the reason for that is that the energy it takes to cause a stacking fault is very low. So there are many, many polytypes that involve different stacking sequences of the silicon and carbon atoms. And depending on the polytype you see, you get a different band gap value. All of them are indirect, but the value of the band gap varies with the stacking sequence. So we did just that and calculate the optical spectra, and we find again that we get a very good agreement with available experiments. Another important semiconductor with an indirect band gap is boron arsenide. And I want to mention this because boron arsenide is one of the largest successes of theory in recent years. So boron arsenide was predicted from theory to have an ultra high thermoconductivity that was second only to diamond. It was a very bold prediction that was subsequently verified experimentally. There was 3 science papers in the summer of 2018 that verified that indeed the boron arsenide has a record high thermoconductivity with only diamond surpassing it. So what we did at the time is we investigated with GeO₂ calculations to find its band gap and found that its band structure looks a lot like silicon, except its indirect band gap is about 2 eV. So that was the prediction for the magnitude, but the material has just been made. So there was no, at the time, there was no measurements of the band gap itself. And so that's when we collaborated with the experimental group of Gang Chen at MIT, who did the optical measurements and found that indeed the calculated coefficients and the band gap agree very well with experiments and verified indeed that the band gap is indeed 2 eV. All right, so I'd now like to discuss what happens once you introduce dopants in a semiconductor. So if your semiconductor does not have free carriers, light can only be absorbed when its energy is above the band gap, in order to be able to excite an electron from the valence to the conduction band. But when you have a doped semiconductor, you have some extra electrons at the bottom of the band, which can also absorb light. And they can absorb light in a direct fashion, like by going to the next band. They can absorb light assisted by a phonon, or they can also absorb light in a resistive process where they behave like they respond to the oscillating electric field, like the way conducting electrons do in a metal. So we factor in all these terms, the direct, the phonon-assisted, the resistive term, as well as scattering by impurities. And we found that all of the contributions are similarly important, both in N-type silicon and in P-type silicon. And if we sum them all together, we get the solid blue lines that you see here that include the contributions by all of the terms. And next, when compared to experiment, we find that indeed we're in very good agreement to experiment over a whole range of wavelengths and doping concentrations. And in particular, we reproduce these shoulder-like features here that comes with a direct transition from the bottom to the next conduction band. And we've done similar techniques also for understanding the absorption of transparent conducting oxides. Again, these are doped oxides with very wide band gaps to exceed the visible range, not to be transparent. And phonons enable the absorption of visible light through this interband process in the visible range. And again, going back to the work on the nitrides I did back in my postdoc, the same thing applies also in semiconductor lasers, where in the laser, the light bounces back and forth in the doped regions of the laser, where it can be absorbed by electrons or holes. And by accounting for how holes can absorb visible photons, we can explain the internal loss in lasers, in nitride lasers at high power. All right. So I'd like to switch now to discussing the process of Auger-Meitner recombination, which is a very important non-radiative recombination process in semiconductors. So what happens in the combination? In the combination is in the material you have both electrons and holes that recombine with each other, and the energy can be dissipated in the form of photons or heat. So in the radiative process, the electron recombines with the hole and the excess energy becomes a photon. But also the energy can be lost to heat through defects in the middle of the band gap, which is known as the shock-delayed hole recombination process. However, if you have an extra electron or an extra hole, there's one more channel where the energy can be lost, where the electron recombines with the hole and the energy gets transferred to that electron, gets kicked up to a higher state, and eventually energy is lost back to heat. This process is important in LEDs, it's important in lasers, and something that I also found out along the way, it is also very important in silicon solar cells. The reason it's important is because it limits the lifetime of the carriers. When you produce an electron in a p-type solar cell, it has to cross the p-type region without recombining with holes. But holes act as traps, they can recombine. So that limits the lifetime. And as a result, it limits the maximum possible efficiency that can be obtained from a solar cell. So that's happening. It's real. The reason it's important for silicon is because the band gap is indirect, so you don't have a radiative rate, and you don't have many defects because silicon is a very pure material. So the dominant process in solar cells today is actually the Auger-Meitner process. And so our goal is to understand how Auger-Meitner process occurs in silicon. Now, let me show it to you in energy momentum space, because there are many ways it can happen. The way you can think of it is an electron recombines with a hole. Now we see this in energy and momentum space. And in order for this process to happen, another electron must take the extra energy and the extra momentum. And that's a direct process. The same thing can happen with two holes and one electron, of course. However, the process can also take part in two steps, where the extra momentum coming from the phonon can enable the transition that would otherwise be forbidden. For example, in this case, when you have two holes, one recombines with the electron, the other will be scattered to this state, but you have no state to go to. So you need this phonon to bring you back to where the band is and enable the overall process. So this work of Kyle that you can find posted on the archive if you'd like to see more details. Before I continue about this project, I'd like to make a brief note on the naming. So this effect is also known as the Auger effect. But however, another person who's worked on this process actually before Pierre Auger was Lise Meitner, who discovered it, who looked at this effect in the context of the internal electrons, the inner electrons in materials. So in the conclusion of her work, we propose that we should acknowledge her contribution in the naming. So we will refer to this effect in the talk as the Auger-Meitner effect. All right, so how about Auger-Meitner recombination in silicon? So you see there are many ways it can happen. It can be direct, through electrons, through holes. And so let's see at electrons first. So what happens when you have two electrons and one hole? The diaphragm experiment are the open symbols you see here. And when we look at the direct process, we get a number that's pretty close to it, in agreement with previous theory and within a factor of 3 from experiment. So one may say that it's good enough, right? However, for silicon, we have very accurate data, so we can go one step further and try to understand if we can improve this. And in fact, we see that if we do factor phonons that enable electrons to occupy any of these final states in the Brillouin zone, we get a much better agreement with experiment across this very high doping range. The situation is even more dramatic for holes, where we see if we don't put phonons and there's no state for them to go to, the direct process is basically orders of magnitude off compared to experiment. And only once we factor in the phonons to enable the transition, we do get this excellent agreement with experimental data. You see some deviation at low densities because that's where we have the Coulomb enhancement effects. And those are the ones that, because you form extons in this situation, but also this can be taken into account with models. We can also predict the depends of temperature, and you see the challenge here is that we don't have good experimental data. The results vary over an order of magnitude, so it's hard to extract trends from experiments, but our theory is within the general ballpark of where experimental data should be. Another thing we can also analyze with our calculations is we can analyze which electrons, which valleys, which phonons participate. So what we see is that The dominant phonons that matter here are the short-range acoustic phonons of silicon, okay, with a frequency of 20 milliV. And when it comes to the valleys of the two electrons, the two of them can be in the same valley, they can be in valleys opposite of each other, or they can be valleys perpendicular to each other. We find that these F-time interval perpendicular valleys dominate, which tells us that by using strain to change the relative energy of these valleys, we can potentially tune and engineer the Auger-Meitner recombination rate in silicon. So again, this is the work of Kyle, and you can see details on the archive. Auger-Meitner recombination, though, is more famous for its contribution to LEDs, in particular the nitride LEDs in the visible range, because they have two major problems. One is that their famous efficiency of more than 80% occurs at low power. And if you go to high power, the efficiency drops. And this is known as the efficiency droop problem of the LED. This efficiency droop becomes even more worse as you go towards the green. And so efficiency is high for violet and blue LEDs and drops when you go to green and yellow. And so a big part of that has to do with the Auger-Meitner effect, that the carrier scattering by the phonons and by the alloy disorder gives rise to Auger-Meitner coefficients in the order of 10 to the minus 31, which do agree with the range of experimental data, and that explains the potential origin of the efficiency reduction in LED. So as we see this cartoon picture here, what we want to happen is we want an electron and a hole to recombine and gives us light, but unfortunately what happens is electrons and holes recombine, and the energy is taken by another electron or another hole, and the energy is lost to heat. All right, so in the third part of the talk, I'd like to discuss about our work on discovering new semiconductors. So how are we doing with time? Is it? Okay, perfect. Thank you. And so I'd like to focus on the ultra-wide bandgap semiconductors. So semiconductors are materials. How would we define a semiconductor? So you may often hear that semiconductors are materials that have gaps which are not too wide, right? An example, silicon, 1 eV, 2 eV for gallium arsenide, aluminum arsenide, but not much more than that. And I want to help you challenge this notion. Basically, semiconductors are any material that you can control its conductivity through doping, and it's efficient, then that material is a semiconductor. So in recent years, we've seen the development of wide gap materials such as gallium nitride and silicon carbide, which are currently used in power electronics. And in fact, there are many efforts here in EPFL as well, developing some of these ultra wide gap materials. But the goal, though, is to go to even wider bandgaps, materials such as diamond, aluminum nitride, and boron nitride, and use them for applications for fast and energy-efficient power electronics, for communications, and for the electricity grid. Now, you may say, why do we want the bandgaps to be wide? The reason is that the Baliga figure of merit of power electronics is what helps us quantify this effect. So the Baliga figure of merit tells us how efficient the semiconductor for power applications, and involves the dielectric constant of the material, it involves the mobility, and the breakdown field to the third power. And the bandgap is important because the wider the bandgap, the higher the breakdown field in a superlinear fashion. So you see that when you employ materials with wider bandgaps, the improvement in efficiency is superlinear, the 6th power or 9th power with respect to the bandgap. And so if you look at the benefits of these wide bandgap materials, you see them in this plot. So take silicon, for example. If you want to make silicon operate at 1,000 volts, you can do it. You can make silicon microchips operate at 1,000 volts. The problem is you have to make them big, and that means that you have to make them very resistive. They act like a huge resistor, and they're slow. So we don't want silicon for power electronics. In fact, this is one of the things that silicon does not do well, no matter the cost. Way better technologies are today silicon carbide and gallium nitride, but the future is to use these even ultra-wide gap materials to improve the bandgap even further and improve the efficiency even more. Now you may say, why am I talking about these 4 materials only, right? So these 4 materials you see are the only ones we have. there are not many ultra-wide bandgap semiconductors, and all of them have limitations. So I want to cover some in this third part of the talk and tell you what we can do to improve the efficiency. So why is it hard to find ultra-wide gap semiconductors? To answer this question, let's look at the difference between an insulator and a semiconductor. So in insulators, the dopant levels are deep, and the energy you need to pay to ionize them is high, much more than kBt. So you end up with an insulating behavior. In contrast, the semiconductors, the dopants are shallow, and they're easy to ionize and give you electrical conduction within the band. A simple way to think about the activation energy is through the modified Bohr model, where you take the 13.6 eV from the hydrogen atom, you multiply by the effective mass and divide by the electric constant square. And now what happens when you increase the bandgap? So there's this universal trend where if you increase the bandgap of your material, the effective mass also gets heavier, okay, almost proportionately. And on the other hand, again, by increasing the bandgap, the electric constant becomes smaller. The material becomes more like a vacuum than a metal. And so, as you see, both of these effects lead to an increase of the activation energy to the point where the dopants become deep and you can't ionize them, and you end up with an insulator. Okay. Not only that, but as the bandgap becomes wider, you are much more likely to form other defects that compensate the charge and consume the free carriers. So overall, this contributes to the fact that doping is much, much harder for ultra-wide gap materials. So, and here's to see it in practice. If we look at diamond and cubic boron nitride, we see that the dopants are quite deep, right? Several hundreds of millieV as opposed to just 45 millieV for silicon. So most of the dopants in diamond and cubic boron nitride are not ionized. The electrons and the holes are bound to the acceptor atoms or donor atoms, and they can't move. Even worse, not only they don't give you free carriers, they also impede those who are there to move. So for example, let's look at here the whole mobility of diamond. Diamond has a remarkably high whole mobility, 2000. That's a very high number, 2000. But that's only true if it's very lightly doped. As you increase the doping, we'll see that this mobility drops down by orders of magnitude, right? So by the time you reach high doping levels where to get low resistivities, you see the mobility drops to the values of 100 or so. It's quite a big reduction. So, and both of these effects stem from the fact that dopants are deep. So that's a fundamental limitation with diamond and cubic boron nitride. You may say, okay, how about gallium nitride, right? I can take gallium nitride, it has a gap of 3.5 eV. I can increase it by alloying with aluminum nitride, right? I can increase it from 3.5 eV up to 6.2 eV. The problem is that this material is an alloy. And because it's an alloy, it scatters the carriers. So we did this analysis where we looked at how alloy disorder broadens the bands. So what you see here is the band structure of an alloy, actually of many, many alloys that we have averaged out. As you see, we can see that once you have this alloy disorder, the bands broaden. There's an average band energy, and there's a band broadening, and this broadening, this energy uncertainty becomes a time uncertainty, a scattering time. And by taking these scattering times, feed them to a model, we're able to find how long a carrier can move in AlGaN before scattering. And with that information, we can find the mobility. So we're able to predict what is the mobility of aluminum gallium nitride alloys as a function of alloy composition. And as you see, alloy disorder causes a dramatic reduction in the mobility. Right? And in particular, it's very strong at the intermediate alloy compositions. So if you factor in both alloy disorder and phonons, we see that the mobility of these alloys, again, is reduced precisely where we want to operate the material. You may say, okay, the mobility is reduced if you put some aluminum into gallium nitride, but then it picks up again. So why don't you work here, right? The problem is that then doping and contacts become more difficult. So that's a fundamental limitation also with AlGaN alloys. These are the non-materials. So what you've seen in recent years is that there's a new material. The beta phase of gallium oxide is currently one of the most popular topics in semiconductor research, as you see by the explosion of citations in recent years. Gallium oxide crystallizes in this structure you see here. Its band gap of 4.8 eV gives you a sizable breakdown field. And most important for experimentalists, it comes in these big wafers that are very, very cheap and very easy to grow. So the devices made with this material show record breakdown fields. But it has its limitations. And I think gallium oxide is kind of a short-lived solution. It's not going to solve all the problems. One is that sure, it has a mobility, but it's 6 times lower than gallium nitride. So it's a more resistive material. So it produces more heat. And although you produce more heat, it's very hard to extract that heat because its thermal conductivity is way too low, a factor of 10 lower than gallium nitride or silicon carbide. So you produce too much heat, you can't get it out, and also you don't have p-type. There is no p-type gallium oxide. N-type is great. For p-type, you form polarons and you can't conduct. So I like to say this material is that for electrons, it's a semiconductor. For holes, it is an insulator. And what's the reason for these factors? The reason has to do with the low symmetry of this crystal. And the low symmetry gives rise to flat bands, low frequency optical phonons that impede the conduction of both charge and heat. So if only the symmetry was higher, those problems could be solved. And that's what we propose to do. So we try to find what is another material that can maintain similar properties to gallium oxide, but have higher symmetry. So we settled on rutile germanium oxide. Okay. Now, germanium oxide, the oxide of germanium, has 2 possible phases. One is the quartz phase that's similar to silicon, right? Tetrahedral, low density, and it also has a more high density rutile phase, which is octahedral, 50% more dense. And here's a crucial difference. This is what I love about material science. The quartz phase dissolves in water. The rutile phase does not. So it's a very cool effect because if you produce the material, you can just, if you have any quartz impurities, you can just use water to wash away what you don't want. This is what experimentalists do, actually. This is true. You can wash away any amorphous, any quartz phase, and you are left with a phase that you want to do. Probably has to do with the polarity of the bond, that the tetrahedral phase is a dipole, the octahedral is not, so that probably improves the interaction with the polar molecules of water. So it's material science, right? This is the beauty of it. And the rutile phase is actually stable in ambient conditions. So we don't want to talk about the quartz phase. We want the rutile also because of its water insolubility and better stability. All right, so why did we settle on germanium oxide? So first of all, germanium is similar to gallium, right? They're next to each other in the periodic table. And also gives a better ratio. Instead of 2 to 3, we have a 1 to 2 ratio. So it gives a higher symmetry structure. We also know that tin oxide is a known N-type conducting oxide. So we know it works. So it's very similar to a working material. But also because of the higher density of atoms, it enables probably higher conduction, both of heat and charge, and even the possibility of p-type doping. So we understand, can we make this? Can we dope this? The first thing we start is with the band structure. And we see things that we like. We see that the band gap is indeed wide, 4.7 eV, although dipole forbidden. So that excludes applications in light emission. We see that the masses are light for electrons. That's what we want to see. But very interestingly, we see that even the valence band has very dispersive bands. So the effective mass of the holes is much lighter than, say, gallium oxide. So we don't expect to form hole polarons here. Potentially can give us to p-type conduction. But is it dopable, right? So to answer this question, we have to go to defect calculation. So a couple of slides here, the methodology we use. We want to study how likely it is to form a defect, a dopant, an impurity in the material. To study this, I have to create a defective cell, say with a vacancy atom here. And I need to compare the defective cell to the pristine cell, where every atom is perfect in its perfect place. And I need to compare the energies of these 2 structures. But I'm not done yet, because we need to account for what happened to the atom we removed. So I need to know the chemical potential of the phase where I move this atom to. And not only that, but my defect may be charged. It may have trapped an electron, may have lost an electron. So I need to account also for the chemical potential of the electrons, which is the Fermi energy. So if the Fermi energy is high, can donate electrons to the defect. If it's low, the defect will give electrons to the Fermi level. And so the methodology is well developed. You can find the details in these two publications. So once you do the calculation, you can find that your formation energy for the defect depends on, first of all, on your Fermi level. So what we see here is the formation energy of the defect as a function of the Fermi level between the top of the valence band and the bottom of the conduction band. And what we see is that as the Fermi level varies throughout the gap, the charge state of the defect varies as well. So this defect may be positively charged, given electrons from the valence band. It can be neutral, or it can be negatively charged where electrons move from the Fermi level to the defect state. And so these charge transition levels are important because they tell us what are the dopant ionization energies. We also need to account for the growth conditions. We can vary the chemical potentials. So by growing in an oxygen-rich environment, say in the atmosphere, or in an oxygen-poor environment like in vacuum, we can change the energy of these defects and control their formation. So we can explore these to extreme limits. All right, so how about dopants in germanium oxide? We do the calculation for many candidates. We look at defects with one more electron than the host, either fluorine replacing oxygen or antimony replacing germanium. And what we see good things. We see that both of these defects are positively charged for any Fermi level throughout the band gap. And that's a good sign. It tells us that these defects will act as donors. They will give electrons that will make it to the conduction band. And the problem, though, we need to avoid nitrogen because that may steal the electron and form a defect. Well, another thing we need to worry also, if we grow in an oxygen-rich atmosphere, like in air, that many germanium vacancies may form, which are also compensating and steal the electrons. So preferentially, we want to operate under oxygen-poor conditions, under vacuum, and use fluorine as our dopant. But other than that, yeah, you should be able to get N-type doping. How about P-type doping, elements with one less electron? We find that, yes, there are. They're relatively more deep. The energy of an ionization is 0.4 to 0.5 eV. So again, not the small numbers of silicon, but they leave the possibility of doping. A bigger challenge, though, is that if you try to introduce aluminum to this material, you are more likely to get an interstitial, aluminum sitting in the middle of the lattice, than to substitute the germanium. So that's not good. It's a self-compensating defect. But what trick can we do? We can use a trick where these defects can form a complex with hydrogen. So hydrogen is also a positive defect in this material. It's positively charged and can bind to these negatively charged acceptors to form this neutral complex that you see here. Here's the aluminum dopant together with the hydrogen. This complex is neutral and has a very low formation energy, which means we can introduce a very high concentration of dopants in this host without compensating by other defects. And once we incorporate those acceptors, we can anneal the sample, remove the hydrogen, and get the P-type dopant. And by the way, this is what happens in P-type gallium nitride, and that's what gave the Nobel Prize to the people who developed the first blue LED. So this trick is known. How about the mobility? We did the calculations for the mobility with the APWQ code, and we found the mobilities are high, both for electrons and for holes. So we do expect efficient conduction for electrons and for holes. So that's what we want to see to enable electronics. So far everything is favorable. So if we put it all together, the electric constant, the mobilities, the breakdown field, what is the Baliga figure of merit we get? We find that the germanium oxide outperforms all current technologies, from silicon carbide and gallium nitride, but also including gallium oxide as well. We find some very high numbers, including for P-type operation. So this is very promising because it outperforms all materials that we know of so far. And how about the experimental side? Okay, so theory predicts this should be dopable, should conduct well. What do experiments say? Experimentally, it has never been approached as a semiconductor before. So the first thing we did is to make some samples. So Sion, the student who did the theory, also did those experiments where she took the quartz powder of germanium oxide. That's what you buy if you order online. And if you hot press it for a few hours and release the pressure, you find that it converts to the rutile phase. And so she measured thermal conductivity, and these are the points you see here. And the red line is the calculations from Kelsey, who did the calculations. And we found surprisingly a very good agreement, even though that was the first time anybody measured or calculated thermal conductivity for this known material. And we see that the thermal conductivity is also higher than gallium oxide, which is another thing we want to do, we want to see in semiconductors. All right, so bulk is good. How about thin films? Because if you want to grow a semiconductor, you need to grow epitaxially thin films to make these layers and get conduction within the plane. So Sion also did experiments. She went to the Cornell Oxide MB facility, the Paradigm facility, and successfully was able to grow single crystalline germanium oxide thin films on top of this tin oxide buffer sapphire substrate. So again, this is the very first report of being able to grow this material in crystalline form. And if you'd like to see more of this work and its implications, you can look at this Invite Perspective article in Applied Physics Letters that we published a couple of years ago. Right, so I'm happy also to share that this work has also been stimulated work by other groups throughout the world. And I want to point out these two results from two groups in Japan. So germanium oxide by itself has not been conclusively doped yet experimentally. That's still an open question or a challenge for us. But what we do know is that tin oxide is a well-known N-type oxide that is doped. So as a first step, I say, why don't we try to alloy the known material tin oxide with germanium to increase its band gap? And that's what these two groups did in Japan. One grid with missed CVD, and the other with partially isolated deposition. So both the groups found that the materials are dopable with a concentration up to 40%. They get nice quality thin films, and they found mobilities which are high, order of 100, which are pretty good for devices. So here's a surprising thing. If you look at the low germanium content, what we see is that as you put germanium into tin oxide, we see the mobility remains high, despite the fact that these alloys do have alloy disorder. So even though there's a random arrangement of germanium and tin atoms that you expect the mobility to tank because of this alloy disorder, we see the mobility is insensitive to the composition. So we're kind of doing work to understand why exactly it's happening. How does the interplay of phonons with alloy disorder gives rise to this apparent insensitivity of carrier transport to disorder? But it seems that this material system has a lot more things to discover, and potentially could be an important new semiconductor that can augment existing technologies. Right. So yeah, this is something that we want to explore. All right. So I hope I will convince you that for over the last 100 years, we studied semiconductors being these hypothetical materials that people had very serious doubts about, all the way to many technologies. And it's a very rich field that has fascinating science, and lots of things to do in the fields of energy, communications, and have an impact on society, where we can apply our calculations to understand and discover new materials. And with that, I'd like to thank, of course, the students who did the work in my group, that you see in the pictures up here, Xiao, Kyle, Kelsey, Siun, Nick, and Makona, and of course, our many collaborators who helped us with these projects, of course, the funding source and the computing resources. And again, thank you for your attention. Thank you very much.
Thank you, Manu. So this was great. And questions are welcome. You just can press the button and mute yourself. Please.
Yeah, hi, Manus. Thank you very much. Very nice presentation. For the case of hydrogen in gallium nitride, the activation rate is quite poor. It's about 1%. So when we want to p-dope gallium nitride, we need to dope quite a lot to get the acceptors that we want. And that at the end degrades the mobility and so on. So the p-GaN is really poor. What do you think will be the activation rate for germanium oxide?
Great question. Indeed, we do see also here that we have a very high energy of ionization we predict. Again, there's some uncertainty in these numbers on the order of 0.1, 0.2 EV. So experimentally, we're still not sure what the exact numbers will be from the experimental side. But yes, we do expect here also a poor ionization. That's indeed the case. However, we hope that we're able to overcome this by incorporating very high concentrations. If you see here, the formation energy of this complex is very low, right? It's like a quarter of an EV and less, right? So what do we expect to see here is when you go to the very high synthesis temperatures, we'll be able to incorporate a very high concentration of aluminum and perhaps get conduction through an impurity band of this material. And there's some very recent work in P-type aluminum nitride even, or AlGaN alloys, where people see some remarkable conductivity at very high aluminum content through the incorporation of an impurity band of magnesium. So I'll be happy to share more work perhaps later with you about how high concentrations of magnesium give rise to dopants that can be activated at room temperature much lower than what we expect based on the activation energy. So yeah, impurity bands may help us here.
So in this, actually it's good, in this doping and co-doping problems, don't you have a little bit of an exponential explosion of all the configurations that you actually have to explore and sample? That is, what do you do usually to deal with it?
Great question. Yes. So how do we study defects and complexes, and where do we stop, right? Looking at combinations, right? So in this case, we start from the simpler complexes first, or individual defects or defect pairs. The reason why you may not form larger clusters has to do with the entropy. So even though energetically defects may like to cluster, there's a much higher entropy by dispersing them all over your sample. So typically in these complexes, the entropy is enough to dissolve them across the material. So it's a great question. We need to keep, in principle, exploring higher orders. I think our safety net is the entropy, that at some point entropy wins and these complexes dissociate. Yeah, so a sign for complex is when you have a positively charged defect and a negatively charged one, so that the Coulomb attraction will bring together to form a neutral object. But once it's neutral, that's when I think the entropy wins, and then you get an uneven dispersion, random dispersion throughout your sample.
Thanks. I think they're torturing students upstairs. It's questions from the audience. So I have from the online audience, we have Vahid from Tehran that asks, is it important to include 3 phonon processes in photon-assisted processes as well?
Great question. Of course, we can go to higher orders in the phonon-assisted optics. So I can go back to that slide. So we can go to higher orders. Usually the phonons, so is it 3 phonons or 3 photons?
3 phonons.
3 phonons, yeah. You can go to higher orders in phonons. Phonons primarily give you momentum, not so much energy. So I would expect to be important only in a very narrow energy region where one phonon does not give you enough energy to make it across the bandgap. But as soon as you have one phonon, that probably gives you any momentum you may need to create transition across the Brillouin zone. What I think will be more interesting to look at is actually when you have multiple phonons. That's something actually we're currently investigating. What happens when you have one phonon and 2 photons? That may be an important source of loss in lasers, particularly in the case of silicon. So that's something that we hope to have some results out soon as well.
And I guess on the same lines, he asks about actually in magnetic materials, if it's important to look at the photon-magnon interactions. Or even if people have looked a little bit at either magnetic or spin orbit coupled.
That's a good question. Yeah, that's a good question. I think in general, yes, one we need to consider it. It would depend on the strength of the electron-magnon interaction compared to the electron-phonon interaction. And so it may depend on a case-by-case to understand it, but yes, in principle, that's something that one would want to consider as well. We'll start with phonons because phonons are universal. Any material has phonons. So for magnetic, it may be a higher order effect that one would need to consider as well.
And I also have a question, so that goes back to all the work done with GeO versus DFT and so on, and it's all about the Fermi golden rule. That is how much it is important to have the delta functions, the conservations on the energies that come from, say, GeO rather than DFT, and that can be very important. But what about the wave function? Are the matrix element important, or we can just trust everything at the DFT level about the conservation rules?
Very great question. Yeah. So for the case of silicon, we're lucky that we know that the GeO and LDA wave functions are very similar to each other. Indeed, in cases where there's a very large change in the wave function, we need to take this into account as well. In those cases, my intuition is we need to probably start with a method that's a better starting point for GeO, whether it's a hybrid or a self-interaction corrected Koopman's approach, perhaps, where your starting wave function and the correct wave function are more close to each other. My philosophy is that if GeO gives a very large correction to the energies of the wave functions, GeO is a perturbation theory. It's a first-order perturbation theory. So if it's a large correction, that probably means that high orders may be also important as well. So maybe a safer bet would be to start from a better starting point so that the corrections are small. Yeah.
But so probably, a finger, because it's difficult to have a fingerprint on how much are the wave functions going to change, but maybe just a hybrid versus DFT could be a good fingerprint for the wave function difference to say if this is important.
Yeah. So remember, for silicon, the early work by Stephen Liu and Mark Hyberson evaluated the wave functions in the GeO picture. And I think that at least for simple semiconductors like silicon, it was a matter of 1% only. But there are cases where it can change by 10% or more. So in those cases, yes, I think it will be much more important. Yes.
Thanks. If there are no other questions from the audience, we thank Manos, Professor Kioupakis again.
Thank you very much.
Very beautiful talk. And as mentioned, Manos will be around today and tomorrow. So just talk with Patrick to set up an appointment, but in particular, he will be visiting us next year. So very good to think at more strategic interactions. Thanks again, everyone.
Thank you very much.